Good morning, everyone. My name is Dushyant Chaudhari. I'm a postdoctoral researcher with Fire Safety Research Institute, which is part of the UL Research Institutes. I'm located in Columbia, Maryland, and I'm excited to be here today to discuss about the modeling the effect of ventilation on fire-induced environment in a controlled gas burner fire experiments which were conducted in a residential structure. So before to start with a little bit of background, in 2017 to 2019, the US Fire Administration found out that the smoke inhalation was a leading cause of fire-related deaths more than thermal burns, and especially in a modern residential building such as the one shown on the top right, which has an HVAC system uh, to maintain a local climate. A fire starting in one region um, can produce combustion products which can be transported through the HVAC duct network. And some experiments have found out that increasing the air tightness of the building uh, creates more underventilated conditions, and also the HVAC system acts as a good transport mechanism for the combustion products. And modeling this behavior is essentially important for performance-based design solutions and also for fire safety. FDS currently has a CFD solver which is coupled with the coupled hybrid HVAC model, and some studies have been performed to validate the capability of FDS to predict pressure development and also the gas transport through this HVAC network. But those studies were especially on a small scale, maybe one or two compartment scenarios, and further validation of the model is necessary, especially for a large scale structure. So the objective of the study was to provide further validation of FDS, and this was done by selecting experiments which were conducted in a large residential structure, which is a two-story structure as shown here on the top right, with a basement and a first floor. And gas burner experiments were conducted in this setup. And one snapshot of an experiment is shown here where the gas burner is in the basement. Along with providing further validation of FDS, the second objective was also to discuss challenges and provide a practical guidance for modeling a fire scenario in an HVAC-equipped structure. So let's look at the experimental setup first before going into the simulations. The floor plan for the residential structure for the first floor is given on the top right, and for the basement is on the bottom right. And both these cases, the duct network is overlaid on the top, which the supply network in red and the return network in pink. Several instrumentation was deployed throughout the structure, such as pressure taps, thermocouple trees, gas sensors, and bidirectional probes. The gas sensors involved quantification of oxygen, carbon dioxide, and water vapor at 1.2 meters above the floor in the locations which are given by these blue circles. And the thermocouple trees measure temperatures from about 1 feet above the ground to 1 inch below the ceiling at every 1 feet interval. The pressure taps, which are shown by these orange pentagons, were used to measure differential pressure at 0.3 meters, 1.2 meters, and 2.1 meter above the floor in these locations. So the 4 experiments selected for the study are labeled as BA1, BA2, BA3, BA4. All of them have 300 kilowatt heat release rate for the burner, which is shown by this red surface simulated in the basement. In these experiments, 2 things were changed systematically: the HVAC status, either off or on. The off status was basically off with only passive transport of gases if there was any. The stairwell door was either open or closed. In the first two experiments, the stairwell doors were open, and for BA3 and BA4, the stairwell door was closed. The stairwell door is essentially the door which separated the basement from the first floor. This structure was built with the help of CAD drawings and PyroSim, and after preliminary analysis of different cell sizes, 10 centimeter cell size was selected for all the simulations. Once the geometry was built for the FDS simulations, two other things were important that needed to be simulated. One was the HVAC duct network, and the other was the leakages from the building, which kind of quantifies the air tightness of the building. So shown here is a stripped down version of the HVAC duct network. Shown in pink circles is the return vents, and the supply vents are shown in red circles. The vents are essentially the vents which connected the duct, the HVAC network with the FDS domain, and between the vents and the fan, which was located at the supply furnace, the S furnace, which was in the HVAC room, there is an intricate simulation of ducts and nodes, which basically try to replicate what was seen in the actual duct network. To simulate the flow through this network, a fan curve, which was based on the manufacturer provided fan curve, was simulated. And the flow through these ducts was then characterized by prescribing loss coefficients to the ducts. The loss coefficients were initialized using the ASTM Fundamentals Handbook, and then the vent flow rates, which was measured before the experiments without the fire, was then targeted to optimize the loss coefficients. The second thing which I mentioned was the leakages from the building structure itself, which was calculated to have an equivalent leakage area of 0.137 meters squared at 10 Pascal, found in accordance with the ASTM E779. This leakage area was distributed on the first floor and the basement by two approaches. First was the zone leakage approach, and the second was the local leakage approach. In both of these cases, the leakage area was distributed in proportional to the fractional leakage perimeter in each zone or for each window or door. The importance of optimization of the loss coefficients in order to achieve accurate vent flow rates when compared to the experiments. This result shows here FDS vent flow rates, the flow rates through the HVAC vents, essentially before and after optimization. Before optimization in green circles, while after optimization results in black inverted triangles. And you can see the vent flow rates after the optimization are match closely with the experimental data than before, especially for the supply vents than the return vents. And the reason why the return vents prediction is not agreeing with the experimental data is unknown at this point, but it could be attributed mostly to the uncertainty of the device used to measure these vent flow rates. But essentially, this is reasonable to say that the HVAC duct network has been quantified well and characterized to move on to the fire simulations. Now, moving on to the results of the simulation, I'll start with the results of the pressure development, some qualitative overview of temperature development, and then the validation results for temperatures. The differential pressure development steady state plots are shown here for the basement and the open bedroom on the first floor, bedroom 2, for simulations conducted using local leakage approach, which provided qualitatively better predictions than the zonal leakage approach in this case. And The two simulations here was for BA1 and BA3, which were the tests where the HVAC was off. But in BA1, the stairwell door was open, and BA3, the stairwell door was closed. What you can see here is that the pressure at closer to the floor is lower than pressure closer to the ceiling in both of these rooms, the basement and the first floor, and this makes sense qualitatively and also agrees with the trend followed by the measured data. Another important thing to note is that higher pressure is also predicted. The first floor has slightly positive pressure as compared to slightly negative pressure for the basement, and FDS kind of predicts this trend as well, which qualitatively makes sense from the fire dynamic standpoint, since the hot gases rise up and mostly leak out from the first floor, and the replenishment air comes in to the basement to sustain the fire, thereby justifying slightly negative pressure in the basement. So the results here show a temperature slice in the basement and the top floor for simulation of test 2, which was HVAC on and stairwell door open. So first thing to notice is that the higher temperature in the basement around the fire, and then slowly traversing transport of gases through the stairwell door. And as you can see on the first floor plot, the gases are flowing due to buoyancy induced flow into mostly bedroom 2, which is the open bedroom. And in this case, you can see that the bedroom 2, which is the open bedroom, has slightly higher temperatures than bedroom 1 and bedroom 3, where the door was closed. Another thing to point out here is the flow rate, or the flows from the HVAC duct as seen by the slightly higher temperatures near the vents, which indicate that hot combustion products are being transported through the HVAC network. Is the steady state pressures at about 400 seconds. That's when kind of the temperatures reach the steady state for simulations second and fourth, which is basically HVAC on and stairwell door open for the test BA2, and test BA4, which is HVAC on, but the stairwell door was closed. So clear difference is basically that the closed door in this case for the test BA4 is severely inhibiting the transport of gas onto the first floor. By the scale for both of these snapshots is the same, 25 to 70 Celsius, and there is a clear difference in the temperature distribution in these two cases. And yet again, there is flow through the HVAC network in both of these cases. So let's look at quantitative predictions of the temperature. This is for test BA, again for the same two tests, BA2 and BA4. BA2 being HVAC on, both the tests, the cases where HVAC is on, and the BA2 is the one where stairwell door is open. BA4 is when the stairwell door is closed. The fire room prediction is pretty similar, slightly under predicting at the later stages. The open bedroom and the closed bedroom, the temperature predictions are similar in both cases. However, and the reason why this may be happening, I'll illustrate that in a bit. I'll discuss that in a bit, but essentially what you can see here is that open bedroom, you can see that the BA2, which was the open stairwell, the temperature is predicted close to what the measured values were at this elevation. But for the closed bedroom, where the transport is primarily occurring through the HVAC duct network, the temperature is over predicted by about 10 to 15 degrees Celsius. And the reason why this may be happening is because the HVAC duct or the HVAC model does not account for heat losses to the ambient inherently, and that could be partially responsible for this overprediction. And to investigate that, further simulations were performed by adding an air coil device to extract heat continuously from this duct, which supplies to BR 3. And the results are not shown here, but the temperature predictions improved and agreed with the experimental data, meaning that including the heat loss from the duct to the ambient is important, especially for the case of non-insulated duct. The predicted temperature rise versus the measured temperature rise is plotted as a scatter plot in this case for all the 4 experiments that were simulated here. And vaguely you can see that the temperature rise predicted is somewhat underpredicted, especially at the temperatures over 100 degrees Celsius, while the lower temperatures is kind of scattered across around the measured values. Essentially, the temperature is underpredicted by about 10% on average. Similar results were also obtained for gas species that were measured and predicted, and those can be found in the upcoming journal publication, for which the manuscript is in preparation. So now I'll discuss some information which was found to be especially important for simulating the HVAC network and the building leakages before moving on to the conclusions. What you can see here is kind of a flow chart which shows a specific phenomena which needs to be simulated, for example, the HVAC network flow, and some important parameters which were found to characterize this network flow was the manufactured provided fan curve, the vent flow rates, and the heat loss from the duct. The manufactured provided fan curve is a flow versus pressure curve, which usually is provided by each manufacturer and can be used to simulate the flow of the fan, the volumetric flow through the fan through this HVAC network. The second is the vent flow rate, which was especially important to optimize the loss coefficients in order to characterize the HVAC duct network. And the last thing was the heat loss from the duct to the ambient, which is not inherently considered or predicted by FDS coupled hybrid model, but can be simulated using an air coil device, especially for non-insulated duct, in order to improve predictions, especially in the closed rooms. The second phenomena of importance was the building leakages, which was essentially characterized using the ASTM E779, which provided an equivalent leakage area, which was then distributed across the structure as a function of fraction parameter of the fractional leakage parameter for each zone or windows and doors. And this was essential to basically ensure that there is accurate pressure development going on in the structure, and also that there are no unexpected underventilated or overventilated conditions. So with that, I would like to conclude that in this study, further validation of FDS was performed for controlled fire in a residential structure equipped with an HVAC system, and qualitatively the FDS predicted the buoyancy-induced flow and the transport through the duct network, but there were several uncertainties in the leakage area, heat release rate, and etc., which might be responsible for some of the discrepancies in the measured and the predicted quantities. And secondly, a practical guidance for setting up FDS simulation was provided, which included the use of experimental measured data to optimize loss coefficients for the duct, using air tightness characterized leakage areas to distribute leakage across the structure, and using the HVAC fan curve for setting up these simulations. Additionally, the heat loss from the duct to the ambient was also found to be an important parameter to accurately predict the temperature rise in the closed rooms. With that, I would like to thank you for the attention, and You can reach me out with question at this email ID given on the slide. Thank you.
I'm not seeing anything in Q&A. Anybody in the room? Any questions for the case study here and validation work? Yeah.
Check.
Hi, my name is Nils Johansson from Lund University. Thank you for a good presentation, very interesting work. Nice to see such experiments. A thing I was thinking about when I saw your graphs is when you had this comparison between the closed and open bedroom. It looked like the temperatures were higher in the room when the door was closed. And that trend, you did not have that trend in the experiment. So my question is, did you measure the flow in the actual vent into that room and compare that between the experiment and modeling? Or did I get something wrong here? Thanks.
Thanks for the question. Can you hear me without any noise issues?
Yeah.
Okay. So yeah, thanks for the question. And yeah, so we did measure the vent flow rates from these experiments, and which was used for parameterizing the duct flow rates for the FTS simulations. And I'm not sure which specific plot you're referring to, where you saw the higher closed room temperatures in the closed room than open bedroom.
It was a case you had 40 degrees C in the bedroom for both cases, both when you had open door and closed door.
Okay.
In the simulation.
Okay. So yeah, I think in the simulation, you're right, and I was surprised by that result as well. And that could be the slight overprediction of the vent flow rates, which are used in the simulation, which kind of averages around the FTS vent for calculating how much flow rate is going through the duct. When we compare the duct flow rates, they match with the experimental data, but the temperature is higher. And that's probably because of this overprediction, and also because the heat losses are not being considered inherently. So most likely the case where the higher temperature is observed in the closed bedroom, it's probably just this compensating effect of buoyancy transport versus transport through the duct.
So you compare the flows in the duct. Okay, that's good. Okay, thank you.
Thank you.
Other questions? No? Okay. All right. Thank you for tuning in for your Q&A. I appreciate it. It's good to see you, and we'll see you soon. Thank you very much.